Greetings. So for today's presentation, will be on label-only model inversion attacks via boundary repulsion. So this paper has been presented or published in the 2022 CVPR conference, and this is a very highly cited paper, and it was published in June 2022. So let's start explaining this paper. So I'll start by explaining the nuances of model inversion or MI attacks and how they differ based on the attacker's access to the machine learning model. So this knowledge basically performs the basics for our understanding the complexity of various attack strategies. So first, there are white box attacks. Here, the attacker has full knowledge of the target model, including its architecture and parameters. In this approach, using a method known as gradient ascent, the attackers can create a model that will they can create inputs that the model will predict with high certainty. Next is the black box attack. So in black box attack, it represents a scenario where the attacker can query the model, but it doesn't know its internal workings. Here, the model's outputs are confidence scores, and this indicates how likely it is that the input data belongs to a particular class. Attackers use these scores to train a separate model, which is called the attack network, to predict the sensitive features. Lastly, is the label-only attacks. And this has been introduced in this paper where the attacker's access is even more restricted. Here, they can only see the final decision that the model assigns to the input data. This is very common in real-world situation as deployed machine learning models don't typically provide the confidence scores of their predictions to the users. However, it also presents a significant challenge since with limited information from the model, designing an effective MI attack requires a more nuanced strategy. In conclusion, label-only attacks is the closest to what attackers face in the real world. And this is the one that is tackled in this paper, and they tackle this by developing their own algorithm. So moving on, I'll go through their main contributions in this research paper. So firstly, the authors created a novel way to figure out private information from machine learning models just by looking at the final output labels and without needing any extra details. Secondly, they provide theoretical proof of the efficacy of their method, especially with simpler models like linear regression. It also looks into how it does with more complicated models like deep neural networks. Lastly, they tested their methods across different types of models as well as datasets, and they showcase that they have better performance compared to the confidence-based black box settings, and they also achieve comparable performance to some of the state-of-the-art white box attacks. In this slide, I will outline the points of their threat model, or basically their approach to MI attacks. So first of all, the attack goal is to recover the original training data. So if you think of an example of an attack on a face recognition classifier, where the goal is to recover the face image for a given identity based on the access to the classifier. So this can be thought of as an attack goal. When it comes to model knowledge, there are three types, which have been mentioned before, and they are black box, white box, and the label only type. So their paper is focused on the last type, which is more closer to real world situations. Text knowledge simply means that the attacker knows what the model is used for, like identifying people in photos. And this is a very reasonable assumption since most models are open about their purpose. Data knowledge builds on this, and so if we know that the model's job, if we know about the model's job, it is easily possible to find publicly available data set that's similar to what the model has been trained on. So for example, if attackers know that that the target model is trained to perform facial recognition, they can easily gather a public dataset of images. One important thing to note is that throughout their experiments, they assume that the public data and the private data, they do not share any classes or identities in common. Target models, so a noteworthy point about their attack is that their approach is model agnostic, which means that their attack can generalize to a variety of models with different architectures as well as sizes. Lastly, target labels means that it is possible to target specific information where the goal is to find a set of images that aim to maximize a set of predefined labels or take a more broad approach. So in their paper, they chose the more precise approach, aiming at specific targets to showcase their algorithm's effectiveness. In this slide, I'm going to explain their break-me algorithm, which is a novel technique for MI attacks in the label-only setting. So the objective here is to understand how to synthesize inputs that a machine learning model will classify with high certainty, even when we only have access to the model's hard labels. So Figure 1 visualizes the steps of their algorithm, and part A begins with a conceptual sphere, as you can see here, within the input space of the model. So they sample points on this sphere's surface, and they query the model to receive hard labels for each of the points. The point here is to mainly explore and analyze the output. The outputs are evaluated to determine which direction away from the decision boundary leads towards the target class's region. So this can be considered the initial compass in the input space. So once the direction has been estimated in part B, the algorithm updates its synthesized input. It keeps querying and adjusting until the sphere sits well within the target class's territory. So as you can see, different spheres have been experimented with, and this finally they come to a point which indicates a higher confidence area. In part C, the objective changes from just approaching the periphery of the target region to converging on its central or most defining part. This is achieved by increasing the sphere radius. As you can see here, the radius of the sphere is increased, and this allows to explore a broader area and gather more detailed information. A broader search helps to better determine which way to go next and make more accurate adjustments to the synthesized input. And finally, part D uh, shows the steps before as are iterated, which progressively refines the synthesized input and approach deeper into the model's confidence zone for the target class. This is continued until it runs out of allowed query attempts or an input is created that is successfully recognized by the model as belonging to the target class. So their research proves that for linear models, the direction estimated by their algorithm actually aligns with the actual gradient direction. And even for deep neural networks, they empirically show that their method can lead to successful attacks, outperforming existing black box approaches and rivaling white box methods. So they also provide a pseudocode of their algorithm. And the main point, or to say it simply, the output of the algorithm is a point denoted by Z star with the largest sphere that can fit into the target class. This indicates that the point is farthest from the decision boundary and is the point used to evaluate the attack. So goals of their evaluation, they try to answer 4 questions. So first question is that can their algorithm successfully attack deep nets with different architectures and trained on different datasets? Next, they try to answer how many queries does their algorithm require to perform a successful attack? Thirdly, how does the distributional shift between private data and public data affect the attack performance? And lastly, how sensitive is their algorithm to the initialization of the sphere radius? So the experimental setup is defined or illustrated in the slide. So the authors experiment on three different face recognition datasets, which is the Celeb A, the first scrub, and the Bugfig 83. So similar to existing work in the literature, they crop the images of all datasets to the center and resize them to 64 by 64. Then they split the identities into public domain, which is used to train the GAN, and the private domain, which will be used to train the target models. Again, there are no overlapping identities between the public and the private domain, which means that the attacker has zero knowledge about the identities in the private domain. After that, the attack is performed on the classifier that is trained on the private domain, and the details about each dataset are shown in this table 1. To study the impact of a large distributional shift between the private and public domain on the attack performance, they use the FFHQ dataset as their public domain to train the GAN and the aforementioned three datasets as the private domains. So here, the experimental setup is continued. So the target models, they use three models, the FaceEvolve ResNet 152 and BGG16, which has been adapted from different papers. For evaluation protocol, they use attack accuracy, which was defined before. They tune their hyperparameters and evaluate against white box and black box attacks existing in the literature. So for results, there are various results. So if I'm going to explain the performance on different datasets, their algorithm is compared to white box and black box methods on three different face datasets, as you can see here. So the FaceNet 64 is used as the target model across all the datasets. For each dataset, GAN models are trained on the public identities, and target models are trained on the private identities. And table 2 shows here, table 2 shows that their approach considerably outperforms both the white box GMI attack and the black box attack on different datasets. So furthermore, their method surpasses state-of-the-art white box GMI attack on Bugfig 83 and achieves a close attack accuracy on the Celeb A dataset. On the other hand, it falls behind only 50% on the FaceScript dataset. So moving on to performance on different models. So this is actually the performance on different models, the table 3. So they use the attack on multiple different models trained on the same dataset. So table 3 shows that the BRIPME algorithm indeed continues to perform well on variety of target model architectures. So it is achieving comparable performance to the white box attack and performing a lot better than the black box attack. So for cross dataset evaluation, in the previous experiments, it was assumed that the attacker had access to public data with low distributional shift compared to the private data. This is because both public and private domains are derived from the same dataset. It is important to consider a more pragmatic scenario in which the attacker has access to only public data that has a large distributional shift. So to investigate this scenario, they experiment using the FFHQ dataset. And this is shown in table 4, where we can see that the accuracy indeed decreases significantly for the Celeb A dataset when we utilize FFHQ as our public dataset. Interestingly, the attack accuracy for Bugfig 83 and FaceGraph datasets increase. And basically, one key takeaway from this experiment is that having a large, diverse public data for inputting a distributional prior is crucial for the attack performance of the model inversion. Moving on, they also investigated the performance of their attacks at various query budgets. This is because in practice, some online models such as Google's Cloud Vision API, they actually limit the number of queries per minute, while others can actually even ban users if they identify an unusually high volume of queries. So due to the fact that some attack scenarios restrict the amount of queries that may be sent to the target model, it is important to investigate the impact of this restriction on the attack performance. And for this figure, demonstrate how their algorithm performs under different query budgets. We see that the attack accuracy increases exponentially when the query budget increases until it goes to a certain plateau. Moving on, a qualitative analysis of their algorithm can be seen in this figure, and it is noticeable that the first generated image at the beginning of the attack is not a good representative for the target class. The progression of the image towards the grounded images is clearly seen with increasing value of radius. Effects of random sampling is illustrated in this slide. So the REPME algorithm starts from an initial random point, and it is important to show whether different initial points would affect the algorithm outcome. So they started 3 attacks with 3 different random seeds of the FaceNet64 model trained on the Celeb-A dataset. And here we can see the attack accuracies, which are around 75%. And this shows that the random initial point has little effect quantitatively on their algorithm. Additionally, figure 4 demonstrates qualitative results, and it can be observed that even under different initial points, the output is close to the ground truth images. In conclusion, in this paper, the authors introduced the BREPME algorithm, which is a novel algorithm that marks the first successful label-only MI attacks. They test across various datasets and architectures and have shown that not only does their algorithm perform well against the top white box attacks, but significantly outperforms black box attacks despite having access to less information. This reveals a crucial insight. There's still much to explore and improve in white box attack methods, and label-only attacks have proven unexpectedly powerful, challenging previous assumptions about what's needed for an effective attack. These findings open up new avenues for enhancing the security and privacy of ML models, demonstrating the critical need for robust defenses. So that is all for this presentation. Thank you.